All right, guys. So you've had a chance to play the game odds or evens with a partner. Should have played 20 games. And then you recorded your results on the whiteboard and had results for the whole class. So now it's time to debrief the activity, and then I'm going to layer on some more formal notes as well as some notation. Okay. All right, let's go ahead and start with question number one. So I played the game 20 times, and here were my results. In the 20 times I played, and remember, we were recording the product, okay? So like if I rolled a 6 and a 5, the product of that is 30. It's an even number, okay? So the number of times I got an odd product was 4 times, and the number of games where I got an even product was 16. Okay? So in the 20 games that I played, right, 4 out of 20 times I rolled an odd, which came out to about 20%. Okay. Now your results are probably going to be different because your 20 games probably resulted in different dice rolls than what I got. Okay. Now when you compiled all your results with the rest of the class, well, I'm not there, so I don't know what the results were. So I'm just going to make up some numbers, and here's what I decided to make up. Right. So let's say the class played the game 300 times, and 64 times odds was the winner. Right. If that was the case, then we would say odds was the winner 21.3% of those games. All right, so now for the first really thought-provoking question, right? Can we say that this percentage here is the true probability of odds winning the game? Okay. And I'm just going to go ahead and flat out say, no, this is not the true probability. Okay. And the reason why I'm saying it's not the true probability is because if we played another set of 300 games, okay, the results are most likely going to look different. Right? If I played 300 more times, I don't think I would get exactly 64 games in which odds was the winner. I might get 65 games where odds was the winner, right? Or it might be 59 games where odds was the winner. So if the results are different, then the percentage that we get is going to look different too. Okay? It's not always going to come out to 21.3%. All right, so this percentage here in question 2 is not the true probability, so what should we call it? We're going to go ahead and call this the experimental probability. Okay. So if you have a red pen or anything different than pencil to write with, label this experimental probability. So this percentage represents the results of playing the game a bunch of times. All right, so if that's not the true probability, then how do we figure out the true probability? Okay. Well, it's not going to come from playing more games. We're going to get the true probability by thinking about all the possibilities when we play the game. All right, and that's what this chart here was meant to help you organize all the possible outcomes when you roll 2 dice and then calculate their product. So the smallest combination you could roll is a 1 and a 1. And then we all know 1 times 1 is 1, so that first product is odd. The biggest combination you could roll is a 6 and a 6. 6 times 6 is 36. That's an even product. Okay? And there's all these other different combinations and their products shown here in the chart. Okay. Now, question 5 said circle all the odd products. I've already gone ahead and done that. So 1, 3, 5, 3, 9, 15, 5, 15, 25 are the only odd numbers in this chart. So there are exactly 9 out of a possible 36 products that are odd. And if you put that in your calculator, you're going to get 25%. Okay, so here's where I want you to add on a couple more notes. So grab that red pen again. The numerator here, the 9, represents the number of ways that odds could occur. So number of ways that we could get odds. Okay. The 36, the denominator, represents the total number of outcomes that you get when you roll dice. Okay, so in this case, there's 36 possible outcomes. So label that total number of outcomes. All right, the percentage we get this time, this one is the true probability, right? It's not the result of playing the games and recording what randomly happens, but this is what we expect to happen based on all possibilities. So we could label it true probability, but I want you to label it theoretical. Theoretical probability. All right, one more thing that I want you to write here on question 6 before we move on to question 7 is some notation. Okay? So mathematicians describe probabilities by first writing the letter P, which of course stands for probability, and then in a few words describing the event of interest. All right, so when we were playing this game, we were interested in odds being the winner. So I'm going to write the word odd here in parentheses. Okay? So this is read as the probability of getting odd. Okay? And we know the probability is 25%, but mathematicians don't write probabilities as percentages. They like to write probabilities as decimals. So we're going to write it as 0.25. All right. So from now on, when we're trying to describe probabilities, we're going to write it using this notation. So start with the letter P, and then in a word or two describe the event, and then the probability, write it as a decimal, not as a percentage. Right, so let's move on to question 7, where we're finding probabilities of other events like rolling a 12, rolling a 15, rolling a 25, etc. Okay. Now I have answers here both as fractions and decimals, okay. And I want to highlight a couple things here. Right. Notice that this probability, if you combine it with that one, equals the probability in part C. Right? That's like 11% plus like 5-ish% gets you about 16%. Okay. Now that shouldn't be that surprising because look at part A, that's rolling a 12, look at part B, that's rolling a 15, and then look at part C, it says 12 or 15, right? So that kind of makes intuitive sense that, you know, if we're just looking at two different outcomes or two different events, right, that we could just add the probability of their individual events. All right, I want you to write this down. Okay, we're just going to write notation to represent what we're seeing. The probability of 12 or 15 is equal to the probability of 12 on its own plus the probability of 15 on its own. Right, look at the next two, which, by the way, there's a typo. This should say D, not B. Oh, it does say D. Okay, so it says B and D, forget it. Okay. So in part D, we want the probability of rolling a 25, and there's only one 25 here in the chart. Okay. And then part E says, now the event is not rolling a 25. Well, that should be everything else, right? So the other 35 outcomes are not 25s. Now, here's what I want you to notice about these. Right? If we were to add those two together, it would just equal 1, because everything's been accounted for. All the 25s and all the non-25s really accounts for all the outcomes. So instead of like counting and getting the number 35, if we had just realized that this is essentially the opposite of that, we could have simply just taken 1, which is the equivalent of 100%, minus the probability of getting a 25, right? And then the difference would give us the probability of not rolling a 25. So what I'm trying to say here, I'll write it in red. The probability of not rolling a 25 could have been calculated by taking 1, or 100%, minus the probability that we did roll a 25. All right, the last question, part F, describes an event where we roll a product between 1 and 36. Well, that's everything, right? Every number in that chart is something between 1 and 36, right? So this is describing the entire sample space or the entire set of outcomes. So its probability should be 1, 100%, right? Everything is accounted for. All right, before we do the quick notes, and I already have them pre-written out to save us some time, I want to show you a little applet, little demonstration. Let me pull it over here. Okay, so we're going to look at something entirely different from tossing dice, which is flipping coins. Okay, and I want you to assume that we're going to flip a fair coin. You can see the probability is 50%, right, for heads and tails. All right, and then let's look at the proportion of flips that land heads. Okay, so I'll start with one toss. Okay, so you can see here, this is a tails, and right now I don't have any heads, so 0% of my tosses are heads. Let's add a second toss. Okay, now there's a head. So in the two tosses that I've done, one was a head, so that's 50%. And you can see the graph started at 0 because that was the proportion after the first toss, but now it's bumped up to 50% because of the two tosses that we have. All right, we'll add a third toss. Okay, so now we've done 3 tosses, but only gotten one head. So that's 33%, and you can see the graph updates. It drops down a little bit, right? And then we can just keep adding more and more tosses, right? Every time we toss a heads, the graph will move up a little bit. Every time the coin lands tails, the graph will move down a little bit. Okay. Let's do a solid 50 tosses, okay? So after 50 tosses, look, we got 25 heads, which is exactly 50%. Hey, that's what we expected to happen, right? That's the true probability, okay? But notice we didn't get the true probability right away. It took us a little while. All right. So notice that at the beginning, when we just did a couple tosses, the probability was like spiking up and then dropping down pretty dramatically too, right? We were at 50%, and then almost immediately after we were like at 15%. And then it bumped up to 30% and then back down into the 20%. So in the short run, right, the behavior of probability is very unpredictable, right? It bounces around a lot. It changes very dramatically after you add a couple more outcomes, okay? But in the long run, right, it stops like spiking and dropping so much, and it starts to get a lot flatter, okay? And now I know we've only done 50 tosses, but what if we did like another 200 tosses, right? Watch the behavior of the graph. Okay. Notice it's not spiking up very high, it's not dropping down very far either. It's just kind of hovering kind of flat, and it's hovering around the true probability, which is 50%. Okay. It's not exactly at 50% because there is, you know, randomness in tossing coins, but it's really close. It's almost there. Okay. And the more tosses we add, right, the flatter the graph is going to look on the right-hand side. Now the left-hand side is still spiky, right? You've got those peaks and you've got those valleys, right? But so in the short run, right, it's unpredictable. But in the long run, you're not seeing that. It's just kind of stabilizing. It's a term that a student last year used, and I thought it was a really good term. So in the long run, probability becomes pretty predictable, right? But in the short run, it's too unpredictable. You cannot really estimate the true probability by doing a few outcomes. You really have to do hundreds, sometimes even thousands of outcomes to get a good estimate for the true probability. Okay, so now that you've seen that app, here are the quick notes for this activity. Okay. So I'll just describe them really quickly, and then I'll have the guest teacher pause the video so you can copy them down. All right, so first, what we were just talking about. In the short run, right, probability has a very unpredictable behavior, right? It spikes up, and then it drops down, and it's just kind of bouncing around a lot because every outcome kind of has a big influence. Okay. But in the long run, after you've done something a couple hundred or 1,000 times, right, the graph was just kind of being pretty stable, right? So it's much more predictable. All right, so there's two types of probabilities. Okay, there's theoretical probability, which is what we expect to happen. Okay, the way you find theoretical probability is not by performing a bunch of trials, but just by thinking about the possible outcomes. Like, what are all the possible outcomes? Let me list them out, and then I'm just going to count the ones that pertain to the event that I'm interested in. Experimental probability, on the other hand, is from doing something a bunch of times and then recording what actually happens. So like in this activity, you and your partner played the game 20 times. Maybe as a class, as a whole class, you maybe played the game 300 times, and then you just recorded what actually happened. All right. This part here is about notation. So this capital P stands for the word probability, and then in a few words you describe the event. I'm just going to be very generic here and just call it event A. And then you find the probability by basically looking at a ratio of the number of ways that your event can occur out of the total number of possible outcomes. Okay, so this is the exact formula that we used in question number 6 here. All right, this last section is about rules of probability. So this is really tailored after question 7. So there's something that we call the addition rule. The probability of one event or another can be found by just adding their individual probabilities. Right? This is exactly what we observed in questions 7a, b, and c. Right? You can add the answers from A and B, and you get the answer to part C. All right, the complement rule is a quick and easy way to find the probability that an event does not occur. So the probability that something does not occur is start with 1, right, or 100%, and then minus the probability of the event. Right? So, for instance, if the weatherman says there's a 5% chance of rain, then automatically you know there's a 95% chance that it will not rain, because in your mind you just did 100 minus 5. Right? That's essentially what this rule is saying. Okay. These last two things are not rules, but more properties. Okay, so probabilities are numbers, and we can represent those numbers as fractions, or as decimals, or even as percentages. Okay, but remember, mathematicians prefer decimals. Okay. So probabilities are going to be decimal numbers between 0 and 1. Okay. So an event whose probability is 0 is an event that will never occur. It's an impossible event. An event whose probability is 1 is an event that will always occur. It's a guaranteed event. All right, the last property is about what happens when you add up the properties for all the outcomes in your experiment. And the answer should be that it always equals 1. Right? So if we look at this, if we look at all the possible outcomes, which is actually what we did in question F, right? Everything's accounted for, so the probability of something happening is 1. All right, so I'll leave it here. Your guest teacher can pause the video. You guys can copy down these quick notes. And then depending on the time, right, if there's a lot of time left in class, go ahead and work on the check your understanding questions. But if there's not that much time, I think the better and more interesting thing to do would be to grab your Chromebooks, and then there's a Desmos activity that you can do. Now, in the last 5 minutes, though, your guest teacher will give you an exit ticket, and you guys will fill it out and drop it in the basket before you leave. Okay. So yeah, if extra time, do the check your understanding questions. But I really want you to do that Desmos activity. That's a higher priority right now.